हेलो। हेलो। Hello. Good afternoon to all of you. Today we will discuss about the four-factor formula. So that is K infinity is equal to eta epsilon P F. So here the way in which neutrons are increased and absorbed, so that we can classify into two main factors, and that is expressed in terms of a four-factor formula. So the neutrons are increased in two ways. One is thermal fission factor and another one is the fast fission factor epsilon. Similarly, neutrons are being absorbed in two ways. One is resonance escape probability P and thermal utilization factor F. So here, just I will explain these four terms, and apart from, finally we will end up with the important four terms. Before that, we will discuss even other important these losses or absorption. So eta is the number of neutrons produced per thermal neutron absorbed in the fuel. Similarly, epsilon is the number of fission neutrons produced by fast neutrons before they are being moderated. And F is the fraction of thermal neutrons absorbed in the reactor. And P is the fraction of neutrons that are in the course of thermalization, or that is the escape being captured by the resonance structure of U-238. So here, that means what are the main characteristics of nuclear fission? That is important one. Two characteristics. One is each neutron induced fission of a uranium nucleus releases a large amount of energy, that is roughly around 200 MeV. And each fission generates 2 or 3, there's an average 2 or 3 neutrons per each fission. So of these 2 or 3 neutrons generated in each fission, if one is utilized in bringing out the fission of another atom of uranium, then the atomic energy is said to have been harnessed. So in such a system, for every neutron used up in fissioning the uranium, another is made available for causing a fresh fission. And in this way, a steady state of self-propagated fission chain, it gets established. So this is the situation. This situation is realized in a nuclear reactor. So this is what will happen in a nuclear reactor. So that means here on average 2 to 3 neutrons are being generated in each fission. So one is utilized in bringing out the fission of another uranium. So that's why one is used up for fissioning the uranium. So that's why this is a sustained chain reaction. So in this, what are the important, these eta, epsilon, P and F. So before arriving these, we will see what are the conditions finally, and each and every term, that is the first one is the, we can consider the average number of fission neutrons, that is nu. So that is the average number of fission neutrons is nu. So this refers to the average number of neutrons thrown out in each act of fission by thermal neutrons. So this nu is 2.4. This nu is equal to 2.44 for uranium U-235. That is for uranium U-235. So that is for 235. And the same, this new value is equal to 2.5 for natural uranium. So that's a technically, there's a U-235 is it is a isotope of natural uranium. So in actual natural uranium, U-235 is only a fraction of 0.72%. So this U-235 undergoes a fission by the thermal neutrons. So for this, you need a thermal neutrons, not fast neutrons. So the effective value is 2.5 in natural uranium due to the fast fission factor epsilon, that is equal to 1.03. So that's why 2.44 into, this is 2.44 into 1.03. So that is equal to 2.5. That it comes about 2.5. So this is the logic behind this 2.5. So in this natural uranium, U-235 is only a fraction of 0.72%. So that is the average number of fission neutrons term. So second term is the fast fission factor. So the fast fission factor, that is epsilon. This is the fast fission factor. That is the fission number of fission neutrons produced by fast neutrons. That is nothing but fast fission factor. So such of the new neutrons, which are all fast, they meet U-238 nuclei before reaching the moderator. So before reaching the moderator, they will hit the uranium U-238 and the fast neutrons. So the effect, the fissions in U-238, and this additional fast neutrons are generated. So that's why the average number of fission neutrons nu, and again you are getting a epsilon, that is the fast neutron fission factor. So that's why at this stage, the total number of fast neutrons increased from nu to nu epsilon, nu into epsilon, where epsilon is the fast fission factor already you know. So this is the value at the second term, considering the second term. So the total number of fast neutrons is increased from nu to nu into epsilon. So third one, that is the fast neutron loss factor. So here what we discuss is the loss. That is the loss because of a, we have to give some provision, or that some provision must be made for loss of a fraction of LF. The fraction, that is nothing but LF. So that F is the subscript F. So this LF is nothing but it is a loss. So what loss? That is the fast neutron loss factor. So after keeping some provision for this loss also, a fraction of fast neutrons, they neither meet U238 nor the moderator, but they leaked out of the system. That is nothing but a reactor. So the fraction of fast neutrons remaining in the reactor is, so that is if LF loss means that finally you have 1 minus LF factor. That is the remaining factor. That is the remaining factor. So this is one important factor. So we will keep it in the other term. So here you have that epsilon is one factor, and nu, initially you have a nu. So this is the after third stage. And next one is the resonance capture loss. So another loss is the resonance escape probability. That is P, resonance escape probability. So the resonance escape probability is the P term. So here, as the epsilon nu 1 minus LF into so many fast neutrons are passing through the moderator. So if the fraction lost through resonance capture is equal to 1 minus P. So that's why you will left with 1 minus P. This is the factor. One minus P. So at this stage, 1 minus P, that is the, if the fraction lost through the resonance capture is 1 minus P. So the number of fast neutrons, or sorry, number of slow neutrons escaping resonance capture will become 1 minus P. So it remains P term only. So it remains P. So next one is the, so at this stage, epsilon nu 1 minus LF into P. So many slow neutrons are available for the next stage. So thermal neutron loss factor. Another loss factor is the thermal neutron loss factor. That is nothing but LT. So that is nothing but T. That is L into T. So this we are keeping another allowance for leaking out of the reactor, a fraction of thermal neutrons. So this leaves behind in the reactor a total number of nu epsilon 1 minus LF into P into 1 minus T. So this is the remaining. If LF is or leaked out, only 1 minus LT remains. So this is the factor which you will remain. That is the total number. So this is nothing but total number. Sorry. So this is it is giving different one, not in English. Okay. This symbol, we are in the symbol range. So this is the times New Roman. So this is nothing but total. Why it is again going back to symbol. Total number of the thermal neutrons of so many thermal neutrons will remain. So next one we will consider the thermal utilization factor, that is the F. We are using F, thermal utilization factor. So a fraction of thermal neutrons are lost by capture by another materials that are present in the reactor environment. So if the loss factor due to these materials is 1 minus F, so loss is equal to 1 minus F. So the thermal utilization factor F of total thermal neutrons available for interaction with U-235 will become nu epsilon 1 minus LF P into 1 minus LT into F. So many neutrons are available. So the next one is the relative fission cross section. So there is a net number of thermal neutrons in the above react with U-235. So there is a total number of thermal neutrons are available, so many. So these will interact with the U-235. But there are interaction is of two types. One is leading to fission with a cross section of sigma F. Similarly, that is a relative fission cross section. So that gives you about the sigma F by sigma F plus, I will write, please wait. So that is the sigma So this is a fraction of sigma f, here sigma f plus sigma r. So sigma r, it is a subscript, and f is also a subscript. So that is a fraction sigma f by sigma f plus sigma r. So this is the relative fission cross section. So this is equal to 4.18 bonds. So that is equal to sigma f value is equal to 4.18 small b. That is a bonds. That is a unit for cross section. And similarly, sigma r is equal to 3.5. Sigma r is equal to 3.5. So this value is equal to 3.5, and all put together it will become 0. The total, this will be equal to 0.544 bonds. So the number of fissions in U-235 in natural uranium is equal to that small k is equal to k is equal to nu epsilon. 1 minute, I will insert that symbol also, that use. So it is a new, finally, the k is equal to nu epsilon 1 minus LF P into 1 minus LT into F. So this is the ultimate or final expression. So here, within this, the 4-factor formula, that is the multiplication of factor K, is the ratio of number of neutrons available for fission in the generation to the available for the preceding, in the preceding section, preceding generation. So that is the, here I will show you. So this is the ratio of neutrons produced by fission in one neutron generation to the number of neutrons lost through the absorption and preceding the neutron generation, the next preceding generation. So that is the total this K represents. So here, this replacing this new sigma, if this also we will add here, and everything in terms of that blue, and here we are using the total brace. So this term sigma f by sigma f plus sigma r into nu So that term we can replace with a eta. So that is the eta. So it is nothing but eta. So eta is equal to nu into sigma f by sigma f plus sigma r. This is the, so that we are representing the number of fast neutrons per thermal neutrons used up. So finally that K is equal to, so now here I will rewrite. It is nothing but, so you can remove nu and this factor. So that is completely represented with a eta. So eta epsilon 1 minus LF, or you can write these things at here. So even you can remove this. It is nothing but n eta p, and f also you can keep. So eta epsilon pf 1 minus lt into 1 minus lf. So here these things for a reactor of dimensions greater than the critical one. So in the critical one means if it is that is the critical size means that is the it is we are making the loss minimum. So we are making that bigger, the reactor a little bit bigger, so that no neutron is escaped from the system. So that's why we can ignore these two terms of leakage factors. So for a reactor of dimensions greater than actual critical one, the loss of thermal neutrons as well as the fast neutrons. This is loss for fast and thermal. LT is for thermal. So by neglecting these two, finally you will end up with these four important terms. And these four terms, we call it as a four-factor formula. That is K is equal to epsilon nu PF. So where the P is the resonance escape probability and eta is the average number of neutrons produced for thermal neutrons absorbed in the fuel, and epsilon is the fast fission factor, and F is the thermal fission factor or fraction of thermal neutrons absorbed in the reactor that are being absorbed in the fuel. P is the fraction of neutrons that are of thermalization escape being captured by the resonance structure. So these are the, finally you will end up with these four factors. So F is the thermal utilization factor simply, and P is the resonance capture factor, and eta and epsilon. So epsilon is the fast fission factor. So that's why these are all the only four final important factors you will left with. So that here we are considering LT and LF are 0. So the value of K is very important in determining the functioning of any reactor. So there are three cases you can consider. So that means this is also we can consider it as a K infinite or infinite multiplication factor. So that is the measure of change of a neutron population from one generation to the next generation. So from one generation to the other generation, what is the number of neutrons that are being multiplying? So if the k infinity is less than 1, what will happen? That is the number of neutrons decreases. So less than 1. So that means it is a convergent case. Convergent means gradually it will become a subcritical and reaction ceases, no more exist. So if k infinite is equal to 1, if the thermal multiplication factor k is equal to 1, so that means no change in the population. The population of neutrons will not increase from one stage to the next stage. So it will become sustained chain reaction. So that is the steady state condition, self-sustaining, or that is the steady state condition. And this is the state where you call it a nuclear reactor attained critical state. That means it is a criticality, attained a criticality. That means whatever the number of neutrons are being produced completely, we are utilizing only one is, that is a gain. So k is equal to infinite factor is equal to 1. And if k infinity is greater than 1, so the multiplication, what will happen gradually from one stage to the other stage, it increases abnormally. So gain is more than 1. So that is a divergent case. So the divergent case, the number of neutrons exponentially increases with time, and it is we call it a supercritical state or divergent state, or that is the explosion will take place. Okay, so that is the major concept of this. So here again, I will come back with the next one. Just please wait. Yes. Any doubts? So we will continue. So here, the next one is, so here the important, the 4-factor formula, and gradually another technically I wanted to discuss about the slowing down of neutrons. So for that slowing down of a neutrons and classification energetically, how do you classify neutrons? So neutron classification on the basis of energy, that we discussed in the previous section. Briefly, I will give you the classification. So that means you can classify the neutrons energetically as slow neutrons, intermediate neutrons, and fast neutrons. So slow neutrons, usually the energy is between 0 eV to 1000 eV. These energetic neutrons are all considered as a slow neutrons. So already extensively studied neutrons at this energy range, and further the slow neutrons you can classify into thermal neutrons, epithermal neutrons, and resonance neutrons. Thermal neutrons, that means neutrons, their energy approximately equal to 0.025 eV. So 0.025 eV. energetic neutrons are called thermal neutrons. So thermal neutrons are very, very critical for nuclear fission. Not the fast neutrons. Thermal neutrons are critical for a fission yield. And second one is the epithermal neutrons. So if the neutron energy is in between 0.5 EV to 1 EV, then these neutrons are all considered as a epithermal neutrons. And next is the resonance neutron. So energy is from 1 EV to 100 EV. So less than 100 EV and more than 1 EV. These neutrons are considered as resonance neutrons. So large number of very sharp resonances are produced in a heavier nuclei when slow neutrons interact with them, and hence they are named as resonance neutrons. So in that particular range, less than 100 EV and more than 1 EV are called slow neutrons. So next category is of a intermediate neutrons. So the neutrons having energy is more than 1000 EV and 500 keV, less than 500 keV. That means 10 to the power 5 EV or 500 keV. So this range of energetic neutrons are called intermediate neutrons. Next one is the fast neutrons. So neutrons with an energy range above 500 keV but below 10 MeV. 500 keV to 10 MeV are called fast neutrons. So usually in any nuclear fission, the fast neutrons usually they will be released or the fast neutrons. So these fast neutrons you have to slow down with a moderating moderator. So that is nothing but a slowing down of a neutrons. So the slowing down of a neutrons, the from fast energetic neutrons to thermal neutrons or slow neutrons, that slowing down without absorbing, that its energy must be reduced to the thermal energies so that the fission yield will be more with the thermal neutrons. So that is the next one is the that slowing down or moderating ratios. So fast neutrons. After fast neutrons, that another fact classification is a very fast neutrons and ultra fast neutrons. So very fast neutrons is energy more than 10 MeV but less than 50 MeV are called fast neutrons. Sorry, very fast neutrons. The very fast neutrons are of the range between 10 to 50 MeV. So they interaction of very fast neutrons with certain nuclei may result then 2 or 3 or more neutrons or neutron proton reactions. For that, very fast neutrons are required. And ultra fast neutrons, so neutrons having more than 50 MeV energy are called ultra fast neutrons. So these are all the important classification of neutrons on the basis of their energy. Next one is the so this is the classification of neutrons on the basis of their energy. So next one is a type of a slowing down. How the neutrons will slow down and what are the important factors, that is the for slowing down of a neutrons. So that for practical purposes, slow neutrons are very useful for fission, not fast neutrons. So we have to slow down the, so that slowing down process is nothing but an elastic scattering by light nuclei. Okay. So inelastic scattering by intermediate or a heavy nuclei is important for neutrons of energy more than 1 MeV. Okay. So that elastic collision between a neutron and a nucleus, you can describe with a reference system. So that is the lab system or center of mass system. So from this, if you use a relation between lab system and center of mass system, and you can derive or you can consider that V naught and V naught minus Vc. So V naught, that is the Vc is the center of mass, speed of the Vc is the speed in the center of mass system. So that is equal to V naught into m by capital M plus m. So by getting into these, we will try to derive the relation between E by E naught. That is the ratio of energies of neutron after and before collision. So after collision E and before collision E naught. So energy before collision and after collision, what is the ratio? So that ratio is equal to E by E naught will be equal to A square plus 2 plus 2A cos phi by A plus 1 whole square. So from this, we can calculate the E minimum, and that E minimum is equal to alpha, and alpha is nothing but here A minus 1 whole square by A plus 1 whole square. So it is ultimately depends on the A, that is the mass number. So from this mass number, we can estimate similarly that theta. So So from this, finally, you can get the relation between scattering angle in the lab system and center of mass system is important for this. So that is nothing but you have a that cos theta is equal to what is the value, or phi is equal to theta if cos theta is equal to theta or theta is equal to phi. So that is for heavy scattering nuclei, the scattering angle of the two systems are almost same. So if the A is the heavy nuclei, then scattering of heavy nucleus, then in the lab system or center of mass system is angle is equal to theta is equal to phi. So another important term is nothing but logarithmic decrement in energy. So that even decrease in energy of a neutron per collision, we can calculate using the term of logarithmic decrement, that is zeta. So where this ratio here, the previously calculated E by E naught, so it is a linear function of theta. With the theta phi, it increases or decreases. So that for all values, E by E naught is almost probable or equal. So that is the probability, that is the initial energy E naught, and how it depends on the range between E and delta E. We have to calculate that E into delta E. So from that, if you calculate the probability and you end up with a zeta that equal to 2 by A plus 2 by 3. So this is the one important parameter where you can calculate the scattering properties of important some nuclei, so that hydrogen, deuterium, and helium, and lithium, beryllium, and for all these things, how many number of collisions are required to thermalization. That means the fast neutrons to decrease to a thermal neutron energy of 0.025 eV. How many number of collisions are required? So if it is in a hydrogen, in almost 18 collisions, the fast neutrons will become thermal neutrons if you use hydrogen. In the same thing, if you use a oxygen, it requires 150 collisions. So that's why the best candidate here, it is the hydrogen is the best candidate, or deuterium. So A is 1 for hydrogen and mass for deuterium is equal to 2, or helium 4. For 4, the number of collisions is equal to 43. So 43 collisions are required for a helium to decrease fast neutron to a thermal neutron. So that's why you can choose the basis of the scattering properties of all the nuclei. So we will discuss the moderating ratio in the next class, moderating ratio and neutron diffusion and diffusion equation, and gradually the Fermi age equation, slowing down, continuous slowing down model, and Fermi age equation.